Hey everyone. Today I thought we could focus in on logistic curves a little more. But first, I have some bellwork solving problems for you. So, uh, solve. Here's the first one. E to the negative 2x equals 6. All right, please solve that equation. All right, did you take the ln of both sides and then bring down the minus 2x? Ln of e is, that's right, 1. And so if we divide both sides by negative 2, we get ln of 6 divided by negative 2. There's our exact answer. We could get a decimal approximation of that on our calculator. Ln of 6 divided by negative 2, and that's approximately negative 0.8958797346, which, we can certainly, since we're doing an approximation, round to 8, 9. Uh-oh, that's going to go up to 6, 8, 9, 6. All right. We could also, of course, solve this equation graphically by doing e to the negative 2x in y1 and 6 in y2. We probably want to set a viewing window that has the y value of 6 in it. So I think standard might work. We saw this is the answer, and that's certainly within our standard viewing window. So let's see what happens when we graph this. Second, calculate, intersect. 1, 2, 3. Yep, negative 0.896. Great. Um, hey, so was anyone surprised that they saw an exponential decay curve here? Remember, it's exponential decay because we have a base that's bigger than 1, and we have a negative in our exponent. Okay, so that wasn't such a big deal. So what about number 2? Wow, this is great. Let's solve this one. 2e to the minus 3x equals 3 times 5 to the x. Okay, now I'd like to, I know I can solve this graphically. I can set this in y1, this in y2, second calculate intersect, and life is easy and happy. That's great. But what about doing this algebraically? All right, so the first thing I'm going to do is, and I'm going to do this one. I might take notes on it in case you see it on our test. It is fair game. You should be able to solve this stuff. E to the minus 3x equals 3 halves 5 to the x. Now, I'm going to take the ln of both sides and use the power rule. So negative 3x ln of e equals ln of 3 halves times 5 to the x. Okay, well I know the ln of e is that, but what can I do over here? Well, the only thing I think to do is to exponentiate. Well, but wait, this confuses me. How am I supposed to solve for x in this situation? It doesn't make sense. Well, so here's the thing. These have two different bases, and I'm kind of stuck. So I took this ln, but I've got an x buried inside of that ln, and I've got this. Oh no. All right, well, maybe a log problem. Would that help? So ln of 3 halves plus ln of 5 to the x. All right, so 5 to the x, I can use my power rule and bring that down. Great, so now I've got negative 3x equals ln of 3 halves plus x ln 5. Hey, I've got an x, I've got an x. Why don't I move all my x's to one side of the equation? So I've got minus 3x minus x ln 5 equals ln of 3x. Great. And now what can I do? Well, I want to get x by itself, so I can factor an x out of each of those terms. And now this stuff is attached to the x with multiplication, so to get x by itself, I simply need to divide. So ln of 3/2 over -3 minus ln 5. In fact, I could even split this into ln of 3 minus ln of 2 over -3 minus ln of 5. Huh. So I am able to solve this algebraically. Okay, let's review what we did there. We isolated the e to the by dividing by 2. Then we took the ln of both sides. We were able to bring this down and have negative 3x, but over here we were kind of sad because we had this. And what I needed to go further in this problem algebraically was to break this up with my log properties. Mr. Doty, I can't talk right now, but I'll call you back as soon as I'm done with this video. All right, so we needed to split this up into 2 logs, and then we could use our power rule, move all the x's to one side, and be done. Okay? You could graph it and solve it graphically. If it's the graphing calculator portion of the test, no problem. We're going to say 2 times e to the negative 3x, and on the other side, 3 times 5 to the x. And zoom standard. There's one graph. There's the other graph. And I could do second calculate intersect. All right. Now, what about this one? This one I think you should be able to do. I would like you to be able to do it. We saw something like this. This is definitely test worthy. So give it a try and show me what you get. Okay, welcome back. Now, did you remember that we talked about writing it this way and then saying that since we have a fraction here, we want to multiply everywhere by that common denominator so that we could cancel out that fraction? If the bases are the same and we're multiplying, what do we do with the exponents? We add them. And so now I'm going to move everything onto one side. 3 to the 2x minus 5 times 3 to the x plus 4 equals 0. And this is a trinomial. And it's going to factor like all those quadratic trinomials we factored. Look, this power is twice that power, and I have 3 terms. So let's go with factoring. 3 to the x, 3 to the x, 4, 1. Positive and negative means both of these are minuses. Okay, so we're almost done. Let's take it a step further. We've got 3 to the x minus 1 equals 0, and 3 to the x minus 4 equals 0. I get 3 to the x equals 1, and then I can take the ln of both sides, or log base 3 of both sides. If I do ln, I can bring this down. X ln of 3 equals ln of 1. The ln of 1 is what? The ln of 1 is 0. So even though I still need to divide by ln of 3, I've got 0 over ln of 3, which is 0. Okay, so one of my solutions is 0. Well, let's see if we can confirm that. 3 to the 0 is 1. 3 to the 0 is 1. And so 1 times 4 is 4. 1 plus 4 is 5. So 0 works. Now, we also have this one. So let's solve that one. We got 3 to the x equals 4. We take the ln of both sides. We bring this down. X ln of 3 is ln of 4. We divide both sides by ln of 3. Don't you dare cancel those out. No. And so this is our second answer. Now, if I get a decimal approximation of this, ln of 4 divided by ln of 3, I see that it's 1.26185. Now, this is exponential. There's no domain restriction on that. I don't have to worry about checking. This isn't a must check. So I'm going to say the two solutions are x equals 0 and x equals ln of 4 over ln of 3. I take it back. It is a must check because this is 1 over 3 to the x. But wait a minute. This can never be 0. This is exponential. There's a horizontal asymptote at 0. So yeah, this is not a must check. But ooh, I did have a denominator, so it's good that I think about it. All right. So let's get on to what we were talking. I want to spend the rest of the video talking about, and that is logistic models. And logistic models generally come in a form like P of t equals L over 1 plus e to the where is it? There it is. C times e to the negative lkt. This is our general logistic form. And clearly, you know, I need to know the carrying capacity, I need to know the rate, and I need to know this value. So in order to build a logistic model by hand, I'm going to need to be given 3 pieces of information to do that, okay? In fact, I think I'm going to write this a little larger and clearer. P of t equals L over 1 plus C e to the minus lkt. Now, I will say this about logistics. We need to do some stuff with logistics, but you won't be doing much until second semester with logistics, except for this algebra review unit. But since logistics show up a little in our spring, and they definitely show up in Calc 2, which many of you will take, I definitely want to spend a little time talking about that now while we're in algebra land. Okay, so remember the graph of this looks like this. It's got y equals L up here. That's our carrying capacity. That's our maximum amount. And then we might have 0, comma. If I put a 0 in here, what do I get? I get, if I put a 0, I get e to the 0, which is 1. 1 times c is c. And so I get L over 1 plus c. So that's always going to be my y-intercept. And we said yesterday, or in the last video, I'm not sure when you're watching them, that this place here, which is halfway between these, y equals L over 2, this is where the rate of change is greatest. In our COVID situation, this could be a model. In fact, this is the model for everyone getting infected. Up here, we have the population of the planet. And here, when we get to half the population of the planet having been infected, that's when the rate at which people are being infected is greatest. Okay, more on our COVID nightmare coming to you soon. So let's take a look at some problems. Okay, I've got 4 in mind for us today. This is actually from Logistic Growth Models, which is assignment 15 in class in the folder. So if you want to follow along. Spread of flu in elementary school is given by P of t equals 100 over 1 minus E, 3 minus T. where t is the number of days after students were exposed to infected students. Estimate the initial number of students infected. So we want to know what is p when t equals 0. So if I plug a 0 in there, I get 100 over 1 plus e to the third. Okay, so what is that? 100 divided by 1 plus e to the third. And I need to close two parentheses there. And I end up with approximately 4.743 students were infected originally. Okay, all it takes is 4 people to come in sick. There's part A. Part B. What is the maximum number of students who will be infected over time? Well, that's easy. C. Estimate the number of days it will take for 99 students to be infected. So I could always do this. 101 plus e to the 3 minus t, and solve this algebraically. And if it's a non-calculator portion of the test, I need to be able to do that. If it's a calculator portion of the test, I need to be able to do that. So let's do it both ways at least once. So the first thing I'm going to do is multiply both sides by this denominator. So that I can cancel out over here. I'm not going to distribute now on the left side. I'm simply going to divide by 99. Okay, so now I have 1 plus e to the 3 minus t equals 1 and 1/99. The reason I wrote it that way is because now I'm going to subtract 1 from both sides. So e to the 3 minus t equals 1 over 99. I take the ln of both sides. I bring this power down. 3 minus t times ln of e equals ln of 1 over 99. Hey, what is the ln of e? Right, the ln of e is 1. We've said that a lot recently, haven't we? Okay, and so I know then that t will be equal to 3 minus the ln of 1 over 99. All right, well, let's see what this is going to be. 3 minus ln of 1 over 99. And I end up with t equals 7.95, 7.595, and these are days. Okay, good. There's part C. I will write my sentence and say it will take approximately 7.595 days for how many students? 99 students? 99 students to be infected. Okay. Next, it says, when will the rate at which the flu spreads be a maximum? Oh, wait, I wanted to go back and do the last one graphically. Okay, so graphically, we type in our logistic model, 1 plus e to the 3 minus x. And over here, we type in 99. And now my window needs to at least get up to 100. I'm going to give a little cushion there and go to 150 in steps of 10. I don't need negative time. And we saw after 7 days, so 10 might be enough for x max graph. There's my logistic model with its 2 horizontal asymptotes. Whee! It's so close to 100. Second, calculate, intersect. 1, 2, 3. And we get 7.595. So we can do these problems both on our calculator and by hand. Okay, now the last problem says, when will the rate at which the flu spreads be max? And then it says, estimate that rate. Okay, so we were looking at a graph, and we saw this, and we know that the steepest place here occurs, if this is y equals 100, then this would be y equals 50. And so my inclination would be just to graph 50 and do second, calculate, intersect, and I end up with 3, 50 here. So after 3 days, the rate at which people are being infected is greatest. Well, fabulous. Now we know that. But now we're asked to find what is the rate there. And so that's saying what is the slope there. And in order to find slope, I need 2 points. I've got 1 point, but I need a second point. Where will I find a second point? And so here's where I recommend using a table. I'm going to take this point wicked close. 3.0000001. Now I can't make up the y value. I have to actually go over to the table and plug in 3.1234567 and a 1. I have to type that number in, go back over onto it, because then I'll see that when this is a 1, this is 50.0000025, right? It's not a 1 there, it's a 25 because I plugged this x value into our function. And now that I have these two ordered pairs, I can find the slope 50.1234565 minus 50 over 3.0000001 minus 3. All right, so let's figure out what that slope is. Divided by 0.1234567. And I end up with 25. And what are the units? Well, these are people. This is time in days. And so this is people per day. The rate at which people are being infected is 25 people per day at time equal to 3. And that's the maximum rate. It's not going, we're never going to have more than 25 people being infected in one day. Okay. Now, in addition to doing these problems, we could also be given this kind of a thing, where we're given a table, 1910, 9.1 million. These are millions of people from my hometown, New York City. In 1910, there were 9.1 million. In 1930, hey, a word about 1910 in New York? My grandfather was there. He was a kid in New York City at that time. And you know what he said? He said that the mail was delivered by a post person 5 times a day. No phones. No phones. 5 mail deliveries a day. You wrote each other letters instead of texting each other. All right. 12.6, 1960, 16.8, 1980, 17.6, 1990, 18.0, and 2000, 18.9, and 2010, 19.5. Okay, So New York's population has more than doubled in the last 100 years. So can we build a model for this? Now, I could say, hey, is this exponential growth? Well, notice the change in population from here to here is bigger than the change in population from here to here. So in an exponential model, the change in the y values gets big and bigger and bigger and bigger. But our y values aren't getting bigger and bigger. They're getting bigger, but there's less distance in between each of them. And so for that reason, I think we're looking at this kind of a situation. So we want a logistic model. In fact, I do not want to build a logistic model by hand, but instead, I want to use my calculator to build me a logistic regression model. So remember, that lives under stat, and we want to start with edit. And in list 1, clear, in list 1, I want to put these, but I don't think I want to put these. I want to make this t equals 0. So this is 20, so this is 50, so this is 70, and this is 80, and this is 90, and this is 100. I'm going to use these inputs. I'm going to build a model for time since 1910. Okay, so I've got 0, I've got 20, I've got 50, I've got 70, 80, 90, and 100. And then I come over here to my list of populations and type in 9.1, 12.6, 16.8, 17.6, 18.0, 18.9, and 19.5. Okay, so to do logistic regression, I do second stat, no, I just do stat. I do stat calculate, and I scroll down until I see logistic. There it is. And again, old school calculator, I'm going to have to type in L1, L2, Y1, telling the logistic regression that it wants to use this for inputs, this for outputs, and it will store the answer here. And with the new model, you want to do that same sort of thing. Remember, it gives you this box once you choose logistic, and you want to make sure that's L1, that's L2. It says store regression equation, you want Y1, and then it says calculate here, and you want to click on calculate. Okay, when I click on enter, I get a logistic model eventually. It's got to think. Trust me, this waiting time that we're doing right now, it's so much less than if we had to do it ourselves. So I've got 19.77117, 469. That's my carrying capacity, less than 20 million people. And then we've got 1 plus 1.15408 1078 e to the negative 0.034821592 t. So there's my model. Now, luckily, didn't I store that here? But I thought I stored it. Oh no. I'm not typing that whole thing in here again. No way. That's crazy. Stat. Calculate. Logistic. L1, comma, L2, comma, Y. Oh, you know what? I didn't do that because I was so busy telling you about it. Okay, enter. There's that wait time again. Okay, same values, but this time my logistic curve is in Y1. And I need that because if I want to say, hey, what's the population in 2020? Well, that would be t equals 110. Let's plug that 110 in for t. I don't want to plug that in and then have to try and figure this out by hand. Instead, I'm going to go over to my table feature and just type in 110. And I see the population of Metro New York should be 19.288 million. We're approaching that carrying capacity of 19.771 million, but we're not there yet. Okay, let's see what the population of New York is now, by the way. Kind of interested to see. Okay, so I'll go over here and ask the happy internet population of Metro New York 2020. And what does it say? Oh, 18.804 million. Wow, we're a little off with our model. That's interesting. Were we really this in 2010? In 2020, well, let's try 2010 and see what it says. I wonder why the population, well, I can think of lots of reasons why the population would decrease. The 2010 census. No, can't find it, and I'm going to stop looking so we can finish this up. All right, let's finish this up and just be, well, our model is a little off. But I will say, when you go to Google and you type in something like, hey, what's the population of New York in 2017? No one was out there counting all the people in 2017, right? You do know that what's happened is we have the census from 2010, and then people build a model of the population of New York, a logistic model, and then they plug in 2017 into that logistic model that was based on the population in 2010. So, yeah, it's only an approximation based on a model, a logistic model that you could do. Okay, so we found New York population in 2020. We found our model was stating the population a little higher than it actually is. Can we find the carrying capacity? How big? Can the population of New York get? Well, we saw on top we had 19.771, and so we know that's 19.771 million people living in the Metro New York area. Okay, B says find when the rate goes from increasing to decreasing. Find when the rate of growth goes from increasing to decreasing. Now that's not when does the population go from increasing to decreasing. It's the rate of growth goes from increasing to decreasing. Well, let's think about what this question means. We know that rate of change or rate of growth is a synonym for slope. And so I want to know when the slope goes from increasing slopes to decreasing slopes. This model always grows, right? It's a rate of growth, always growing. Always, the population is always increasing. But we're asking when do the slopes go from increasing slopes, meaning the slopes are getting bigger and bigger, to decreasing slopes, meaning the slopes are getting less big. Okay, so here I have close to a zero slope, and here my slope is a little more positive, and here my slope is a little more positive, and then I get to this point. And after this point, the slopes start getting more, they get smaller and smaller. They're still positive, but no slope is bigger than the slope here. So this question that was asked about when does the rate of growth go from increasing to decreasing is the same as asking when do we have max growth rate? And we know how to find the maximum growth rate. We know that the y value here is L over 2, so 19.771 over 2, but I don't know this value. And how do we find this? Well, we go over to our calculator, and we go to y2, and we type in 19.771 174689 divided by 2. Okay? And then we graph. Huh. There seems to be an error. Well, let's go find out. 2. The logistic model looks good, but it wasn't graphing. Oh, I didn't have parentheses. Okay. And my window, my y-max doesn't need to be 150. My y-max can be, I don't know, 25 in steps of 1. And we know we need at least 100 years on this, so I'm going to go with 150 years in steps of 10. Okay, so here's our graph. And there's our L over 2. Second, calculate, intersect. 1, 2, 3. And isn't this interesting? The maximum population occurs when t equals 4.115, which was 1914. Why, that's at the height of the tenements, where all those poor immigrants were living in lower Manhattan at the turn of the last century, when they came from mostly Europe, but not only Europe, to find a better life. It was around this time that my grandparents' family came over. So, yeah, that's very consistent. City was growing fastest at that time. You know, you go to a place like New York now and you say, big city, lots of people. But it's not it's growing, but growing very slowly. Growing fastest. Wow, that's an exciting city, ever changing. Well, we have done a lot of things with these models. Now, what I'd like you to do is you do your homework. And your homework tonight with assignment 15 is over here. Your homework is exponential and log rewriting worksheet. My guess is you're going to have questions about that, so please ask those questions. I think especially, I think you should be good on 2, though I'm a little worried that you didn't take good notes in the last 2 videos, which would help you with 2 and with 3. 3 is the one that I think is most tricky, and then you got a word problem for number 4. Okay? So let me know what your questions are, and hopefully we can get them out of the way in GroupMe, if not in a live Zoom. All right, take care, everybody.